Now let's look at how to multiply matrices. So we know how to take the matrix of a composition of linear transformations. This guy is defined because we know what well, that was bad. We know what ST means, and in terms of transformations, and given a transformation, we can always find its matrix for a given basis. So let's look at the definition of matrix multiplication. Now this is going to be defined precisely so that this MST is going to equal the matrix of S times, with the matrix multiplication we're about to define, the matrix of T. So if we've got an M by N matrix A, and we've got a N by P matrix C, we're going to define the product. Oops. And we need to specify what its entries are, right? So the jkth entry of the product is going to be the sum r equals 1 through n of a, j, r, c, r, k. And so in case that looks like a horrible formula, the way to keep it straight is that the thing that you're summing over, those are the inner dimensions, so-called. And that's what we see right here also. So it's the ones that are sort of next to each other. So the n comes last there and then first here. So these guys are connected. And so this is commonly referred to as saying inner matrix dimensions must match. So that's what's going on there. And so in this terrible expression right here, you can think of it as kind of like the R and the R's, which are right next to each other, cancel to leave the jkth entry. Okay, fair enough. Let's move on now to the promised result. So this is 343 in the book, and it says that for a linear transform T from V to W and S from U to V, so we need to have the codomain of S match with the domain of T for this to make sense, as usual. Then the matrix of ST, the composition, is the same thing as the product, the matrix product of the matrices of the two transformations. So here, the operation between S and T is composition, and here it's matrix multiplication the way we just defined it. Okay, and so this is why we defined it that way, because we want this to be true, because it makes many nice things happen. So let's look now at the proof. And so we will let A be the matrix of S and C be the matrix of T, and we will let V1 through Vn be a basis for V, and W1 through Wn be a basis for W. And I guess we also need U1 through UP as a basis for U. And I just realized I messed up. That should go up to W sub M, not W sub N. Okay, so then as K goes from 1 through P, so we're looking at things in the final image of all this, the range of all this rather. What does st applied to the kth u vector look like? Well, so this is s applied to tuk by the definition of s as composition. And from the definition of the matrix of T, we have that this is actually going to be the sum r equals 1 to n crk vr. Okay, and so that's coming from how the entries of C express the action of T on the basis of U. And then we could use the linearity of S, right? Because those capital C's, those are just numbers. This is this thing inside the parentheses right here. This is a linear combination of vectors. So we can use our property of linear maps, pull out the scalar multiple CRK, and this is S applied to VR. Okay, and so here I've just used the fact that S is linear. And then next we have, let me just rewrite this first part here. And now if you look at S applied to VR, well, A is the matrix that tells us what that looks like in terms of the W's. So this is going to be times, and then here we've got the sum k equal, sorry, not k, we need something else. J equals 1 to m a j r wj. And so this is because the entries of A express the action of S on the basis of V in terms of the basis of W. And so then these are finite sums, so I can rearrange them whichever way I like. You can always reorder a finite series. There's no problem there. And then also A times C is the same as C times A when we're talking numbers, and that's exactly what they are. These things here are scalars, and our field is commutative, so I can write this as a JRCRKWJ. And then if I parcel this part off in the inside, then I see that that's just the formula as was given for matrix multiplication. So that's the jkth entry of AC. And so now, reading from the very beginning to the very end, this shows that the entries of AC express the action of ST on the basis of U in terms of the W's. And that does it.